Welcome you to my lecture today. Today we are actually going to start chapter 9, which is the last unit in the semester. This is called Logistic Regression. Today, before I get started with this topic, I think I'm going to have a recap on what we've been doing before. I told you initially we find ourselves in a world where we actually want to take a decision that we're not going to regret. We basically want to take economic decision, political decision, medical decision, and so on like that. And taking a decision that we're not going to regret, we need to be able to understand our environment. The facts remain that we live in a stochastic environment. We live in a probability space where different things happen in different days. And we basically, because of that, we actually want to model, we basically want to capture reality using a mathematical expression, which we call model. And I said from day one, model can never give us an exact reality. Model will only lead to approximate reality. Okay, at times we may want to build a model, a statistical model, to characterize relationship between variables. But let me tell you this, there are different kinds of statistical models that we can use. But I want to tell you now, the model, the kind of statistical model we're going to use depends on the nature of the data set. I remember when we're trying to characterize the relationship between two variables, where the response variable is continuous. Okay, the predictor variable, which we call the explanatory variable, could be either continuous or categorical, but you know what? The special requirement to use a linear regression is that the response variable has to be continuous. Continuous. What do you mean by continuous? A continuous variable, when data can take infinitely many values, okay? Infinitely many values. An example like height, the weight, the amount of sugar in an orange. The amount of sugar in an orange, it could take so many. The amount of times an athlete used to run maybe 100 meter or 200 meter, there's so many values for that. So what I'm trying to talk about now, when the response variable is continuous, and we basically want to fit, we're trying to understand relationship between variable, we're basically going to use linear regression. And let me tell you this, I walk you through a situation where the simple linear regression can also be extended to multiple linear regression, where you're going to have more than one predictor, and situation also where you're actually going to incorporate a nonlinear effect into your model, whether the quadratic or the cubic, or at times the interaction effect into your model. The fact remains that when you are dealing with a simple linear regression or multiple linear regression, the response variable that we call the outcome variable must be continuous. From there, we move into analysis of variance. The special requirement of analysis of variance, in addition to the assumptions that you have in the analysis of variance, is that the response variable, which is the outcome variable, also need to be continuous. Look at that. That is the similarity. between regression and the analysis of variance, the nature of the response variable has to be continuous, only that in analysis of variance, the predator has to be categorical. I'm going to say this again. In analysis of variance, the predator has to be categorical. But you know what? We also have situation where one of the factors in the analysis of variance can also be continuous. Can somebody tell me for extra credit? Situation where one of the predator in analysis of variance can actually be quantitative or continuous. What is the name we're going to call that instead of analysis of variance? Can somebody tell me now, whether online or in person, what name are we going to call that model? Whether online or in person, what name? Well, I'm going to repeat my question now. In analysis of variance, we require that the predator has to be categorical, right? And I said we could have situation whereby in addition to the categorical predator, we could have a predator that is quantitative. Only that the analysis of variance, we have to have a change of name. Can somebody tell me the name for extra credit? You're very close. There's a particular name instead of analysis of variance. You try, yeah? You said what? Also very close. It is also going to be called analysis of something, but it's not going to be called analysis of variance anymore because the predator is one of the predators is categorical. You also have another predator that is not categorical, that is continuous. Can somebody remind me? That is what we call, let me check whether I have a response online. Okay. Analysis of covariance. Good job. Look at the word co. Look at that. Analysis of co. Look at the word co. It means in addition to the categorical factor, we also have quantitative factor. Exactly. Send a message to me for extra credit. And those of you who mentioned something as well, send a message, but I'm going to give you a half point. You try, you share. Okay. Now, you can see now. But you know what we want to do today? What if in a situation where the response variable is no longer continuous, but the response variable is categorical? This is the first time, okay, in our lecture in this semester that we're going to talk about when the response variable is no longer continuous, but categorical. That is what we want to do today. Okay, now in the outline today, I'm going to talk about linear probability model. Okay, what is the meaning? Why do we consider logistic regression? To model a categorical outcome. Why not linear regression? When you use a linear regression for categorical outcome, that is what we call a linear probability model. But there's a problem with linear probability model. And that is the reason why we actually we go for logistic regression. I'm going to show you today the problem encounter when you make an attempt to use linear regression for categorical response, because that is not appropriate. You're basically going to say the problem that we encounter. Then I'm going to introduce it to simple logistic regression. Okay, then I'm going to talk about how do we implement the linear probability model in R, and how do we implement the simple logistic regression in R. Now, I want to start with linear probability model. Now, let me tell you this. In linear probability model, let me just tell you this, I said this time around, we basically want to model categorical outcome. Let me give you an example of a categorical outcome. You apply for student loan. What is the outcome? You got two possible outcomes. It's either you're going to be granted or not. And if you are going to be granted, they're going to consider some predictor, right? They're going to consider your ability to pay, and they're going to consider whether you're actually going to do well. They're going to look at your past academic performance and some other predictor variable like that. So which means the outcome variable is categorical, which means that you are given the loan, you are granted the loan or not. Another example of categorical outcome is this. What if in a situation, I know when some of you are done, you basically going to apply to graduate school. And applying to graduate school is either you are going to be given admission or not. But there are some factors they're going to put into consideration before you can be given admission. I know they're going to look at your GPA. Okay, they're going to look at your GRE score. They're going to look at the prestige of your undergraduate school. They put into consideration some predictor. So which means what the school want to do is to classify applicants into being admitted or not admitted. The outcome variable in that situation is categorical. Now, take a look at me now. We basically want to build a model where we already know those who are admitted. We know the status of the applicant. We know some of the predictors. Then we can build a model. On that, I'm going to call that model a classification model, where we can use the model to predict a new applicant. For instance, if I know the predictor of a new applicant, like what is the GPA of the new applicant, what is the GRE, what is the prestige of the undergraduate school, then when I plug in that into the model, we can actually predict whether it's going to be given admission or not. That is the essence. Classification based on certain attributes that we observe on the participant or on the applicant. So I think I've given you so many examples of. I think I'm also going to give you the one in sports. If you look at the outcome variable, like it's either you win a match or you lose a match. Okay, though there's some situation where match could actually result into draw. In that situation, you're going to have three categories. That is the categorical outcome, which is now subject to what is the probability of winning a football match? Oh, maybe it depends on the way you attack or the way you defend and so on like that. But at the end of the day, you're going to have a categorical outcome. Now, by linear probability model, initially we started using, when you use linear regression to model a categorical outcome, we call that linear probability model. I'm going to say that again. When you make an attempt to use linear regression that you've done to model a categorical outcome, I told you the linear regression is only appropriate when the response variable is continuous. But initially we made attempts to use a linear regression on that, and we call that linear probability model. But you know what we experience using the linear regression? I mean, for the categorical to model categorical outcome, what we encounter the violations. When you use inappropriate model, what is going to be the consequence? The consequence is assumption violations. And that is basically how we know, whether a particular model is appropriate or not. A very good model will not lead to violations of assumptions, but inappropriate model that will lead to violations. What is the number one thing that we notice? There's basically going to be an heteroscedastic error. You know what I mean? In the assumptions of linear regression, we expect a constant error variance, right? But there's going to be a violation of that. And not only that, the error will not be normally distributed. You can investigate that. I think I've walked you through how to investigate whether the constant variance is violated. You can use a Bartlett test or Levine test. And you can use the residual plots to be able to investigate that. What about normality of residual? Of course, you can do the histogram of residual. You can do a normal KK plot. You can also conduct Shapiro-Wilkie test of normality. That is how to know. What I'm trying to tell you now, there's going to be evaluations of all these using the linear probability model, which we call the conventional linear regression model, for categorical outcome. Another potential problem is that you're basically going to have potential nonsensical predictions. You know why? Because the outcome variable, which is y, is going to be between 0 and 1, because we're going to have a label. When you are giving admission, we can label that 1. Not giving admission, we can label that 0. Because don't forget, your response variable is categorical. Do you know that when you use a conventional linear regression, your prediction will be outside this range? You could have a negative prediction. You could have something more than 1. And that doesn't really make sense, because the range of the categorical response should be between 0 and 1. And using linear probability model, which we call the conventional linear regression model, there's going to be your prediction is going to go outside this range. Okay, now what are we now going to do for our prediction not to go outside this range? Let me tell you this. There's possibility. We can solve the problem of heteroscedasticity. We can solve this problem when we do sampling distribution. But you know what? There's a problem that cannot be solved at all, which is this, because your prediction is basically going to go beyond 0 and 1. And what is the only way to solve that is to we need a brand new regression model. And let me tell you this, I used to tell people there is nothing new under the sun. You know what we normally do? We reparameterize, we modify. Okay, I'm going to show you, if I want to go from linear regression to logistic regression, I'm basically going to use a transformation. You remember the other time that whenever there's a problem, okay, with the response variable or with the behavior of residual, we normally transform, right? We're also going to do a transformation here, because I'm trying to tell you now, the transformation of linear regression will lead to logistic regression that we can now use to model categorical outcome. Okay, now this is what we are looking for. When you use a straight line, when you use a linear regression, it is going to go over the boundary. Take a look at, okay, I'm going to see if this is going to work. Okay, those of you online, you can see what I wrote, right? You saw that, right? Okay, can somebody confirm if you're seeing that I'm using my iPad? Okay, thank you so much. Okay, now, when you take a look at this line, this is a boundary, because the outcome should go from 0 to 1. But when you use a linear regression, it's a straight line, right? The linear regression, the line is going to go, without bound, which means there's possibility the line can be here and the line can also go over that. You know what we're looking for? We are basically looking for a model that we actually have this kind of shape. You see the shape right now, right? That is what we're looking for. And you know what? There's something I want to walk you through an example now. And you know what? Before I can achieve that model, I need to do a logit transformation, which I'm going to show you. But I want us to do this. I want to use this as an example. I've already attached this particular data set. You can check the wiki level model. This is a Titanic data. Everybody have heard about Titanic. I know most of you have heard about Titanic story, right? Where some survived, some did not survive. Now, we have a lot of, the categorical, the response variable here is categorical, right? It's either a passenger survive if there's an accident, it's either a passenger survive or not. That's a categorical outcome, right? Now, we got some variables here, predator variable. We got this passenger ID, the survivor, the P class, the name, the sex, the age, and so on like that, the ticket, the fare, and so on like that. Those are the variables. You know what I want to do now? I want to look at the effect of fear, the fare you pay, okay, the fare on whether a particular passenger is going to survive or not, which means I want to actually consider one predator, right? And you know what? What am I doing here? I'm trying to use a linear regression. What did I call linear regression? It is not appropriate. You know that, right? It is not appropriate because the outcome variable is categorical. The linear regression is only appropriate if the response variable is continuous. Okay, but you know what? I decided to ignore that, and I want to see what is going to happen when I use linear regression. Now, I got this result. Okay, now when I got this result, what is the interpretation now? The interpretation is just that the PI, because when you take a look at what I have here, I'm going to write. The outcome variable is not continuous; it's categorical. We're going to call it probability. Why? Because it's from 0 to 1. Now, here now, the probability of surviving is 0.31 or 31974 plus 0.024907 fear. Okay, you know what this guy is trying to tell me now? What that guy is telling me is that the PI here is the probability that the passenger will survive. Okay, he said when fear is paid 0, for this time, when fear equal to 0, when the passenger don't pay any fare, right? We want to interpret the intercept, right? If you want to interpret the intercept, you're going to multiply this guy by 100. Okay, it's going to tell you, we expect that the probability to be 31.97% if the passenger don't pay any fare. Okay, now, and what about this guy here? The model predicts that each additional pound of fare is paid is associated with a 0.25. How do I get that? You multiply this guy by 100, and when you multiply by, you're going to have 0.25 to, when you approximate. That was how we got that. You get that now? Now, I'm going to show you when you now plot. Let us see what is going to happen using the linear probability model. Oh my God, take a look at that. Using the straight line, what happened now? It goes completely out of the range. The range is supposed to be, look at the dotted line. It's supposed to be between 0 and 1. But using the linear probability model, which is a conventional regression model, it doesn't make sense at all. Now, the meaning of this, let's see a lot of violations. You can see some clustered line here, right? Look at that. Look at this one. Okay. Look at this one. There's no constant variance. Look at that. There's no constant variance. That's a violation of a constant variance. And not only that, because the straight line actually go beyond the boundary, then there could be potential nonsensical prediction. And that was why I refer to this region as a nonsense region, because it's not in the response. The response is from 0 to 1. Using the linear regression model for categorical variable, it will lead to violations. And I told you the other time, a model is as good as assumption put into a model. If assumptions are violated, then we cannot trust model. In this situation now, using a linear regression model for categorical outcome, that is going to lead to assumption violations. And that is the reason why we needed a brand new regression type model that can handle that. Does that make sense to everyone how linear regression is violated? Where we know when you use that on categorical outcome variable. If you're good, can you say yes or you just okay? Those of you online, can you confirm if you are still hearing me clearly? Those of you online?
Yes.
Okay, good job. Thank you so much. Now we needed a brand new model where that would be within 0 and 1. That we have an S shape like this. Okay, how can we achieve that? I'm going to show you now. I think I've already told you. You know what I'm doing now? Comparing the linear regression model for categorical outcome with a brand new model that we call logistic regression. Take a look at it too. This is going to go beyond. It's going to go beyond the boundary, but that guy is going to be within. Look at that. Okay. So that is a different. And I want you to pay attention to this. Look at the range 0 to 1, right? 0 to 1. When a response variable is categorical, okay, it's going to be in the range of 0 to 1. Okay. Now, because of that, I present to you a new type regression model that can be used to model categorical outcome, which is what we call logistic regression. And I'm welcoming you now to logistic regression model. Okay, logistic regression model. Of course, the response variable has to be categorical with 2 or more levels. When you have 2 levels, like applying for mortgage loan, it's either you are giving or no. That is 2 levels, right? We call it binary logistic. Binary logistic. Okay, that is where you have 2 levels. When you have more than 2 levels, we could have situation where we have more than 2 levels, right? Maybe you're trying to talk about the satisfaction of customers about your service. It could be not very satisfied, satisfied, uh, very dissatisfied or dissatisfied. How many levels is that? 4. Situation where you have more than 2 levels, we're going to call that multinomial. Multinomial. You got, the outcome variable is more than 2 levels. Okay, we're going to call that multinomial. When the outcome variable is 2 levels, we're going to call that binary logistic. But you know what? Before I go into how we derive logistic model from the linear regression, I need to first inform you that we got different types of logistic regression model. Number one, we have a binary logistic regression where you have a 2 dichotomous outcome. Okay, so that there's a spam. It said that the message that come in go into your inbox or or it's a spam or going. You get what I mean? So which is either this or that, 2 levels. And like I said, we also have a multinomial logistic regression. And we have different kind of multinomial logistic regression, in situation where you have more than 2 categories. And we also have ordinal logistic regression. The ordinal logistic regression is when you order. Now, I'm going to give you this example now. If you take a look at multinomial, we're talking about 3 or more, but they are not ordered. Okay? But when you talk about ordinal logistic, you talk about, 3 or more, but they are ordered. I'm going to tell you when we get here, what do we mean by ordering levels of categorical variable and not ordering that. Okay. I think I gave a lot of example. I think I've given you an example today. Okay. One of the example of logistic regression in politics. You suppose that we are interested in the factor that influence whether a political candidate wins an election. Of course, the midterm election is very, very close, right? where politicians are now going around, to disclose their manifestos. Okay. But you know what? Because we find ourselves in a world where we are too anxious to predict the future, we basically want to know what is the probability of a candidate winning an election. It's either if a candidate, if a politician actually competes in an election, it's either the politician win or loses, which is categorical response. Then we can use logistic regression. So that's an example. Only that we need to identify what are the predators. Maybe the amount you spend on campaign or the amount of time spent campaigning negatively, and whether or not the candidate is an incumbent, because incumbency actually play a role at times. Now, this is another example. You are, researcher is interested in how variables such as GRE, which is called the graduate record exam score and the GPA, and the prestige of your undergraduate institution, you're looking at the effects of that of getting admission into graduate school. The response variable is categorical. Okay, there's a lot of examples of logistic regression model, but you know what? I basically want to show you the model. How does a logistic regression model different from linear regression model? Oh my God, I want you to pay attention now. This is where we're going. In a linear regression model, I'm going to show you what you're going to see. What you're basically going to see the model. If I'm talking about simple linear regression model, you see the response, y. Okay, this guy here is continuous. Don't forget, it's continuous, right? And this guy here can be continuous or categorical. It doesn't really matter. Now, let me tell you this. There is a linear relationship between y, okay, and the predator. But let me tell you this. We basically, because when you apply linear regression on categorical outcome, there's going to be violation, the violation of constant variance, the violations of normality of residual, and not only that, we could get potential nonsensical prediction. That will not, a prediction that won't make sense at all. Now, what are we going to do? What we're going to do is we need to consider transforming linear regression model. We need to transform this. And what are we going to transform? We're basically going to transform what caused the problem. The reason why we cannot use this model for categorical outcome, okay? Therefore, what we need to transform is the response variable, okay? What we need to transform is the response variable. You remember when there's a violations the other time, when I was walking you through transformation, you remember a time we could do the log of response, right? But when you do the log of response for categorical outcome variable, that will not achieve results. Now, what are we going to do? We need to do the logarithm of the odds. Because of that, I'm going to tell you what we mean by odds. Okay, I'm going to tell you the meaning of odds. Some of you may want to know what is the difference between odds and probability. Let me tell you this. When you are talking about categorical outcome, the odds will tell you the chances in favor of an event to the chances against the event. I'm going to say that again. Odds, chances in favor of an event, okay, and chances against it. Okay, but what about probability? This is what the likelihood occurrence of an event. There's a difference between these two, and I'm going to tell you why. I'm going to quickly give you one example now. If in a bag, if I have the numbers of red in the bag is 4, and the numbers of black is 6. What is the probability of red? You know, when you want to talk about probability, you are talking about occurrence divided by a whole. Occurrence divided by a whole. The probability of red will be 4/10. But if I want to talk about odds of red is different from the probability of red. Now, let me tell you now, in the odd, we're talking about occurrences divided by non-occurrences. Now, if I want to talk about the odd of red, okay, the odd of red now will be 4 divided by 6, which is number of red divided by the numbers of not red. The number, so here it's going to be 4/6. This is the odd of red. But the probability of red is going to be 4 divided by the totality. And because of that, we're basically going to say occurrences divided by whole. Look at the difference. Okay. Now, here, odds can go from 0 to infinity, but the probability go to 0 to 1. You see the difference between them? Now, why are we using odds? We're using odds because when the categorical variable, the response variable is categorical. If you apply for student loan, okay, then there's going to be odd. The odd is going to be whether the probability of you being considered for the loan divided by the probability of not, which is going to be odd. That is what we mean. And if you take a look at that now, pi is the probability of being considered. 1 minus pi is the probability of not being considered. When you apply for admission, it's either you are giving the admission or you are not giving the admission. And the odd ratio now is going to be the ratio of the probability of you being given the admission divided by the probability of not giving the admission. And you know that the probability of success and failure, success and failure are mutually exclusive. Therefore, they're going to add up to 1. And that is the reason when you see a pi, then divided by 1 minus pi, pi means the probability of success. 1 minus pi means the probability of failure. When I do the log transformation, when I do the log of that, okay, the log of the odd ratio is linearly related to the predictor. I'm going to say that again. The log of odd ratio is linearly related to the what? To the predictor. And let me tell you this. It is only when you have a linear relationship that will not lead to violation of assumptions. I'm going to say that again. Anywhere in the world where the relationship is not linear, okay, whatever effort we do to make it we try to do other effort to make it linear. Okay, that's what we're doing. Now, right now, what can achieve linearity now, okay, is when I take the logarithm of the odd. If I don't take the logarithm of the odd, that will not be linearly related to the predictor. And, taking the logarithm of the odd ratio, that is what we call the logic transformation. The logic transformation of linear regression lead to logistic regression. I'm going to say it again. Logic transformation of linear regression lead to logistic regression. And what do I mean by logic transformation is basically the logarithm of the odd ratio. And where do I get the odd ratio? Odd ratio is just the levels of the categorical response. Okay, now there are 2 ways we can write logistic regression. In logic form, which is the log of pi over 1 minus pi equal to that, or in probability form, which is pi equal to that. So we got 2 ways of writing logistic regression model. Okay, but let me show you this. when I'm writing it this way, I'm going to be referring to the beta naught and the beta one as the log odd estimate. When I'm using the logit form, log odd estimate. Okay, now you know what I'm going to do now? That same problem that I did the other time, where I'm trying to look at the effect of the fare paid by passenger on survivor. Okay, you know, we use a linear probability model, and we realize that actually lead to violation of absorption. Then I'm going to use logistic regression now. Oh my God, I want you to pay attention now to the code of logistic regression model. Model 2, GLM. You know, in the linear regression, you're going to see LM, but in the logistic regression, you're going to see GLM. What do we mean by GLM? That's a general linear model, because we do a transformation of a linear model to become a logistic regression model. So you got a GLM, survival on fear. Data, I'm using my data. You have to specify family equal to binomial. Why do I say family equal to binomial? Because binomial, we use binomial distribution to model a dichotomous outcome. Don't forget, we are dealing with a dichotomous outcome. What do I mean by dichotomous outcome? Outcome that is binary in nature. That could be this or that. That's what we mean. Oh, let's take a look at the result now. This is the result now. And I want you to pay attention to something. When you are running linear regression, you're going to see T value. When you are running logistic regression, you're going to see Z value. Look at that Z. Do you see Z value? Okay, those of you online, you can see Z value. When you are dealing with the logistic regression, we don't talk about T value. I'm going to show you now. I'm going to take you back to when we run the linear regression. You're going to see T value. Do you see T value here? Okay, the T value, okay, will come with the linear regression. But when you run logistic regression, it is not going to be a T value. It's going to be a Z value. Pay attention to that. Okay, you can see Z value. Okay, and we have a different way to assess logistic regression model. You're going to see as part of the output, you can see the AIC. Okay, you know, the other time we talk about a model with the lowest values of AIC is a very good model, right? Okay, our AIC is going to come out with the null deviance. I'm going to tell you what is the meaning of null deviance. The null deviance is just talking about when I'm looking at the probability of survival without considering any predator at all. While the residual deviance is trying to tell you when I'm looking at the probability of survivor, okay, you know, here the response variable survivor, you know, putting into consideration fear, putting into consideration predator. So the distance between the residual deviance and the null deviance can also be used to judge, you know, to assess the quality of a logistic regression model, which we're going to do on Wednesday. Okay, now you have a logistic regression model now. Let's assume that you are given this. Please, I want you to pay attention. Everyone, please pay attention from this model now. If I ask you to write estimated logistic regression model, I can ask you a question. I can say, okay, write it in a logit form or write it in a probability form. I'm going to start with writing this in a logit form. In a logit form, take a look at this logit form. In the logit form, it is log of pi 1 minus pi equal beta naught plus beta 1. Hey, so if I want to write this now, I'm going to say log. Okay, pi is probability of survivor, right? The probability of survivor divided by 1 minus the probability of not surviving, right? Probability of not surviving equal, what is beta naught? Minus is 0.896828 plus is 0.015997 fear. Look at it. This is how to write logistic regression in a logic form. At times, you can write this. You can just write y cap 1 minus y cap is allowed minus 0.89 08284 plus 0.059 fear. Now, this is writing logistic regression in logic form. What if I asked you to write it in probability form? I'm going to take you back now, okay, to the probability form. The probability form is that pi, right? Look at that. You know what I'm going to write? In probability form, this is what I'm going to write. I'm going to write, I can write pi, or I can say y cap, that's no problem, okay, equal exponential raised to power minus 0.89, is 0.890828, okay, plus 0.01 5957 fear divided by 1 plus that. Can you see that? This is in probability form. You see that? You know what we're going to calculate with this? If I know the fare, amount of fare a passenger paid, if you plug that in, we can determine the probability that that passenger will survive. It's just like if I'm applying this to student loan, if the predictor variable is your credit score, it means if you are given the credit score, we can predict the probability that you will be given the loan. So that is why we have the logic form and the probability form. Now, how do we interpret? How do we interpret, the estimate? Well, let me tell you this. When you run a logistic regression model, this estimate, you know what we call them? The way they appear, we call them. I'm gonna write now. We call them log hard estimates. Minus is 0.896828 and is 0.015997. They are called log odd estimates. I want you to take note of that. Now, how are we going to interpret them? I said the coefficient, the standard error and the z statistics are called the worst z statistics and the associated fever. So fear is statistically significant. How do I know that? How do I know it's statistically significant? Because the p-value is it's less than level of significance, right? At 0.05. Then I said, the logistic regression gives the change in the log odd. I wanted to take a look at that. Log odd of the outcome, okay, of 1 unit increase in the predictor variable. For instance, if I want to interpret the fear, I'm going to say the log odd. I'm going to say for every unit in the amount paid by the passenger on fare, the log odd, look at what? The log odd of survivor versus non-survivor increases by that. Look at that. What am I doing? I'm interpreting this guy here. I'm interpreting the estimate. Whenever I want to interpret that, I must mention the log odd. Okay. Now, we can also get the confidence interval for the coefficient estimate for the log odd. Okay, you just write the confit model, it's going to give you that. Okay, then we can also talk about odd ratio. Odd ratio. There's a difference between the log odd and the odd ratio. How can I remove the log from the odd? If I want to get the odd, mathematically speaking, I'm going to take the exponential. But if you want to do that now, look at that. That's what you're going to do. ESP. We give you odd. Now, how can we interpret this now? The odd ratio 1.0161258. What are we trying to say? We can say that for a 1 unit increase in fear, the odd of being survived to not surviving increased by what? Increased by this. There's a difference between odds and the log of odds. It means passengers are more likely to survive because you are looking at the ratio of survivor to non-surviving, but very, very, when the ratio is one, you know what I mean? When the odd ratio is one, who can tell me? When the odd ratio is one, 50-50, it's rising. Look at that. Assessing logistic regression, I think I told you, we're going to use our p-value to be able to justify inclusion of predator. So this is where I'm going to stop today. Do we have anybody want to ask question before I go today? Okay, so see you on Wednesday. Your midterms grade will be released on Wednesday. Okay.